Dear students, welcome to the next lecture of electrical measurement. So in the last lecture we discussed the topic of AC bridges. Okay, so let us before going further, let us just have a quick look of what we discussed in the last lecture. So we basically started with the topic of AC bridges. Okay, so if this is an AC bridge, okay, having four different arms having the different impedances. These are maybe Z1, Z2, Z3, Z4, okay, and there may be a detector which is placed here in this position, okay, and there will be a voltage source or I think the voltage source will be placed here, okay. So this is the voltage source. So the difference of an AC bridge with that of a DC Wheatstone bridge was that in balancing an AC bridge, the two different conditions have to be met, okay. So if we just represent the impedance in the form of, let's say, Z theta, okay, so I have just put this bar here because it's a complex quantity. So this represents the magnitude and this is the phase angle of the complex impedance, okay. So this can also be written in this form because in AC bridges, what is the condition of balance? That the product of the magnitudes of the opposite arms impedances should be equal. So that means that this Z1, Z4 should be equal to Z2, Z3, okay. So there can be two things in this. We can also write it in this form if we also write the angles here. So this will be Z1 theta 1 multiplied by Z4 theta 4. This should be equal to Z2 theta 2 multiplied by Z3 theta 3, okay. So what should be the two different condition? One condition will be that Z1 Z4 should be equal to Z2 Z3, and there will be one more condition. What is that? That theta 1 plus theta 4 should be equal to theta 2 plus theta 3, okay. So these two are the conditions for bridge balance, conditions for AC bridge to be balanced, okay. So this is the difference between the AC bridge and DC bridge. This is what we discussed in the last lecture, that is the product of the magnitudes of opposite arm must be equal, and the second condition is the sum of the phase angles of the opposite arms must also be equal. So with this discussion, we also discussed the Maxwell inductance capacitance bridge, okay. First of all, we discussed a simple form of Maxwell bridge which do not include a capacitance, and next we also discussed this form, that is the Maxwell inductance capacitance bridge, which contains a capacitance in this circuit, okay. And we also discussed that this Maxwell inductance bridge is only used for the measurement of medium Q coils, where this Q is the Q factor, okay. So because we cannot use for this bridge for the measurement of high Q coils, okay, because for high Q factor coils, because this condition of phase angle has also to be satisfied. So if the coil would be having a high Q factor, then that means the phase angle of that coil will be very nearly 90-degree positive, okay. So we are talking about this coil here. This is the unknown branch, this is the coil, Okay, so if it is having a very high Q factor, then the phase angle will be very nearly 90 degree in positive direction, and which requires that the phase angle of the capacitance arm must also be very nearly 90 degree to cancel out each other. Okay, so this is the coil arm and this is the capacitance arm. So just to satisfy this condition of phase angle equality, if this is 90 degree in positive direction, so this must be also be 90 degree in negative direction, only then it will cancel each other. Okay, so this in turn will mean that the resistance which is associated with this capacitance, that is this R4, it should be very large. Okay, so that is why it can be impractical for high values of Q factor. It can only be measured for medium range of this Q factor coil. So this was the reason. Now next we move on to the next type of bridge circuit which is used for the measurement of inductance, and that is Hayes bridge. Now this is the circuit of the Hayes bridge, okay, which is shown here. That is, this is again the unknown coil or the unknown inductance, okay, this L1. So this is different from the circuit that was used for Maxwell's bridge, obviously. Okay, in this circuit the capacitance is connected in series, whereas in Maxwell's bridge the capacitance was connected in parallel with the resistance. Okay, so now you can see from this circuit that for large phase angles this value of resistance should have a low value. Okay, so that is why we can say that this Hayes circuit is more convenient for measuring the impedances for high Q factor coils. Okay, now the bridge balance condition can be achieved in the same way as we had done for the last cases as well. Okay, so this I have already told you that this L1 is the unknown inductance. Let us just write it down here. This is the unknown inductance, okay, having this fixed value of resistance which is shown here as R1, this R2, R3 and R4, these are known resistances. So these are known resistors, okay, and this C4, this is a standard capacitor. Okay, so let us now just try to derive the balance conditions for this circuit. Okay, before that we can also try to first draw its phasor diagram. So I am just drawing it alongside this figure. This may be taken as the reference, this I1 or I3. This is I1 omega L1, this is E1 equals to E2, and this can be extended as I2. Okay, similarly in this direction it will be I2 over omega C4, this will be 90 degree. So it will be just in straight line with this. So this should be the resultant E. So this is simple just by analyzing this circuit analysis, different current and voltage, you can see that whether they will be in phase with which of the quantities. Okay, so now let us just try to uh, see the balance equations. So at balance condition, so now in all the AC circuits, whether it will be the inductance measurement circuit or the capacitance measurement circuit, you just have to follow the basic governing equations for the AC bridge balance equation. Okay, so what we have discussed in the very first slide in previous lecture, or in this lecture also, I just had told you that these are the two balance conditions which have to be met. Okay, so at balance, this R1 plus j omega L1, this is the impedance of this coil, multiplied by R4 minus j over omega C4, this is the impedance of the fourth branch. This should be equal to R2 R3. Let us simplify it. Now from here, after this step, you can just separate the real and imaginary components in this expression. So separating real and imaginary terms. Okay, so what you will get after separating the real and imaginary terms, R1 R4 plus L1 over C4 should be equal to R2 R3, and L1 should be equal to minus R1 omega square R4 C4. Okay, so you solve the above two equations for L1 and R1. So for L1 you should get R2 R3 C4 over 1 plus omega square C4 square R4 square, and for its resistive part, that is R1, it should be omega square R2 R3 R4 C4 square over 1 plus omega square C4 square R4 square. Okay, so you can also try to solve these equations and get the resultant, you can say, expressions for L1 and R1, because this first branch was the unknown, this which you have to determine, L1 and R1. So you should get the final expression of L1 and R1 in terms of the other parameters. So you should also try it yourself to get these expressions. Okay, so Q factor of coil, as I already told you in the last lecture as well, that it is nothing but it is the ratio of omega L1 over R1, or you can also just represent this Q factor for the RC circuit as well. So it will be 1 upon omega C4 R4. So this is the quality factor. So this L1 and R1 have been obtained as this. Okay, so if you have the value of these different components like R2, R3, C4, R4, so you can find the value of the unknown inductance. Suppose in any problem, if it is given that there is a circuit having this much magnitude of these components, you just find the value of L1. So you just substitute all the values in this given expression, and you can get the value of the unknown inductance as well as the unknown resistance. Now from this balance equations, one thing we must discuss, that both these terms of L1 and R1, they have this frequency term in their expression. So it means that the frequency must be accurately known before carrying out the calculations. Okay, now let us just try to do a little bit modification in these expressions, as I had defined the Q factor to be 1 over omega C4 R4. So let us, if I just try to substitute this in the given expression of L1, let's see what I will get. So this L1 will come out to be R2 R3 C4 over 1 plus 1 over Q whole square. Okay, now for the higher values of Q, let's suppose when Q is greater than 10, okay, or may have some even greater values. So for these higher values of K, this term actually becomes very small, and therefore it can be neglected. So if it can be neglected, then the approximate expression of L1 comes out to be R2 R3 C4. Okay, so that means that when we have to measure the inductance of the coils which are having very higher values of Q factor, then it is not necessary to know the frequency of supply, as just we had discussed here, that although this term of frequency is coming here, but if we are measuring the inductance of coils having higher values of Q, so it can be neglected just by having this assumption, and the required expression just simplifies to R2, R3 and C4. Okay, but on the contrary, we can also say that for those coils for which the Q factor is low, is on the lower side, then in that condition this Q value or this term cannot be neglected, rather this have to be considered. Okay, so in that case you can go for the Maxwell bridge, as that will be more suitable than this Hayes bridge method. Now let us move to the next type of the bridge, and that is known as the Anderson's bridge. So this is again a bridge circuit which is used for inductance measurement. Okay, again you can see from its circuit that it's a modification of the Maxwell inductance capacitance bridge. Okay, and now as there is some changes as compared to the Maxwell's inductance capacitance bridge, which is quite visible from this circuit. Now here this L1, again this is the inductance which is to be measured, so this is the unknown inductance, this L1 is the unknown inductance, okay, and this capital R1 which is shown alongside here, this is the resistance of this inductor, okay. So resistance of inductor, and this R1 which is shown here, that is this R1, small r1. So this is a resistance which is connected in series. So this is a resistance connected in series with L1, okay, and all the remaining resistances, that is this R2, this R3, R4, and also this small r, all these are known resistances. So this R2, R3, R4 and small r, these are known values of resistances, and this C, this is a fixed capacitor. So this is a standard fixed capacitor, okay. So all these are components of this Anderson's bridge. Now let us try to derive the balance equations for this. So again we will just try to derive the balance condition by taking the same conditions which was discussed for the AC bridge balance, okay. So at bridge balance, the I1, this I1 should be equal to I3. So this is the I3 which is flowing in this branch. So this, although this is shown as I1, but you can just correct it to be I3. So at balance condition, this I1 should be equal to I3 and I2 should be equal to IC plus I4. So you can just see in the circuit that this is I2, this is I2, and this is IC, and this is I4, okay. So this must be the sum of these two currents. Now I1 R3 should be equal to IC over j omega c. That means IC equals to I1 j omega c R3, okay. And the other balance equations, if you write the other balance equations, so that will be I1 times R1 plus R1 plus j omega L1. This should be equal to I2 R2 plus IC small r and IC r plus 1 upon j omega c will be equal to I2 minus IC times R4, okay. So substituting the value of IC in the above equations, what we will get? We will get so you substitute IC in above equation. Let me just write it down on next page. So it will be I1 times R R1 plus R1 plus j omega L1, that should be equal to I2 R2 plus I1 j omega C R3 times small r, okay, or you can simplify it, R1 plus R1 plus j omega L1 minus, so j omega C times R3 R equals to I2 R2. So what you have done in this step is just you bring this parameter on the left hand side of this equation, so then it will be j omega C R3 I1 R plus 1 upon j omega C, this is equal to I2 minus I1 j omega C times R3 R4, or I1 times j omega C R3 R plus j omega C R3 R4 plus R3 equals to I2 R4. Okay, so let us call this equation as equation 2, and you call this equation, that is this equation, as equation 1. Okay, so from both these equations, from 1 and 2, so from equation 1 and 2 you should get I1 R1 plus j omega L1 minus j omega C times R3 R equal to I1 R2 R3 over R4 plus j omega C times R2 R3 R over R4, plus there will be one more term, this is j omega C times R3 R2. Okay, so now after this step you just have to separate the real and imaginary terms, as we do it so often in this bridges circuit. So R1 will be equal to R2 R3 over R4 minus R1, and L1 should be equal to C times R3 R over R4 small r R4 plus R2 plus R2 R4. Okay, so just by looking at these balance equations you can see that to obtain easy convergence of balance the alternate arrangements of this R1, that is this R1 and this R, it should be done as they appear in only one of the two balance equation. Okay, so that means that if you change R1, only this parameter will be affected, okay, as this R1 is not present in this equation. Similar for this small r also, that if you just vary this just to obtain balance, then it will only affect inductance, it will not affect this value. Okay, so this is actually a advantage of Anderson's bridge, especially when we have to measure the inductance of low Q coils. Okay, because in case of Maxwell's bridge we had seen that for low Q factor coils there is a problem of sliding balance, okay, which we discussed in that. So that problem is eliminated in Anderson's bridge for low Q coils. So that is why we can say that if we are measuring the inductance of low Q factor coils, then Anderson's bridge is the preferred method over the Maxwell's bridge, as the problems related to the convergence of balance would not be present here in this Anderson's bridge method, but it was present in Maxwell's bridge. That's what we had seen. But at the same time, there may be a disadvantage also of this circuit, that it is slightly, you can say, more complex than Maxwell's bridge. Okay, and the balance equations are also slightly complex than the Maxwell's bridge method. Okay, but still it is the preferred way or preferred method of measuring the inductance of coils with low Q factor. Okay, so low Q coils, for low Q coils this method is preferred. Okay, so we had seen 2 or 3 methods for the measurement of inductance. We had seen the Maxwell's bridge method for inductance measurement, we had seen the Hayes bridge method for inductance measurement, and the Anderson's bridge also we had discussed. Okay, so all the 3 bridges have their advantages or disadvantages, and they have their applications in different for different you can say coils. Okay, so for medium values of Q, the Maxwell's bridge is preferred. For high values of Q factor, the Hayes bridge method is preferred, and for low values of Q factor, the Anderson's bridge is more preferred way of measuring the inductance. Okay, so this is all about which we have to discuss in this lecture. Now the bridge circuits for measuring the inductance that are over, and in next lecture probably we will try to discuss the bridge circuits that are used for measuring the capacitances. Okay, so this is all for today. Thank you very much.